Thanks. So first of all, I just want to give some references. These are the main sources for everything I'm talking about. Let's leave it at that. Second of all, in the morning, I actually wrote down a very complicated formula at the end, but I failed to introduce one piece of notation there, which none of you noticed, which, okay, it makes sense. It was a complicated formula. But this one is quite important. Because this is really where we start seeing that X is the topological recursion X. So recall that I always use mu to indicate the connected component, or the irreducible component, I should say, of the curve. So we have an index mu, that makes sense, but we also have this index A. And I'm going to sum over indices which are not integers here. And that's where things get interesting. So I'd already introduced just J of X. J of X was some current of this Heisenberg VOA. But these are really the twisted modes. And that's where Newton's comment came from last time. And of course, I also need to actually give you the twisted modes then. So note that k is not an integer, but our mu times k is an integer because, well, basically how we define it. So what we do now, we have these variables x mu k. So that's going to be similar as before. And we also have these things here. So the positive and the negative modes are basically the same as what we have had before, but now we all label them with the irreducible component we're at. Okay, less than 0. But this is kind of interesting. We can also add 0 modes now. So I'm going to do this. Where q mu is just some complex number. And note that because of our grading convention, all of these are of degree 1. That's why I wanted to have this h bar to the power 1/2. And, well, why do we introduce this? One argument is because we can. It's a generality we can use, and this is one of the motivations of this talk anyway. But it turns out that in examples, Q can actually play a role, and hopefully I'll get to that. We do, apparently, this is a condition we'll find later, but I'm going to say this already. We will find out that we need this sum to be 0. This is going to be imposed later, but it tells us that if we have a usual irreducible spectral curve, or at least locally, these Qs do not play a role. So in the usual story of TR, we don't see them. And it's really a new feature we have. But okay, we can now add that, so we do. Right, that was just final comments on the last talk. And now I think I'm at section 2.3. Which should be dilaton shifts. And polarization. Yeah. The mu. So what we had, the spectral curve you should think of is a product of x minus z to the mu r. Mu going from 1 to d equals 0. This is the geometric picture you'll have to keep in mind. Right, so this is also, because these are not integer powers of x, where these mu actually turn up. So the way to interpret this is actually by taking the right z on the right component. So this j mu, it is associated to a particular component. On this particular component, we do have an r mu root of x, because that is what z is on this particular component. And that is what I mean by these non-integer powers. Right, okay, so just a reminder of this morning. I told you that we wanted to have these WIKs, or we had these WIKs, and we wanted to somehow interpret them as an array structure. But there was an issue because WIKs are homogeneous, and hence the degree 1 condition is very far from being satisfied. Okay, so what do? We try to break up this homogeneity. And that is what a dilaton shift does. What we do is we want to we want to literally shift some of these modes by something which is not of degree 1. Because note, every one of these modes is of degree 1. What we can do is we can shift them by something of degree 0. And that will break up the homogeneity of these more complicated WIKs, which I'm not going to rewrite. But hopefully you've got them written down somewhere. Okay, so how do we do this? How do we shift a mode? Well, the algebra here is fairly simple because we have all of these things, and well, for different mu's, they commute. So if you have j mu and you have j nu, these will always commute. So only if we have the same upper index, they may possibly not commute, and that is if the sum of the indices between the two is 0, right? Because the derivative operator acting on a variable, that will not be 0. So how we use that, we basically commute, or we conjugate with the exponent of some of these modes, and that is what's called a dilaton shift. Now I'm going to introduce some more notation, and this is geometrically minded. So actually, I'm going to take an omega 0, 1. And omega 0, 1 will be a 1 form on this spectral curve. But to be clear, we need to now define this on each component. So I'm going to use this notation to indicate the components and then the variable z. So for each component mu, we have to basically give a function. So this is just shorthand for giving a couple of functions, one on each component. And as everything is local and algebraic, I'm just going to give you a power series. And the notation for these things, for the coefficients, is this. So this is part of our initial data, as usual. I'm going to add some more. Because we have this possibility of q's now, and half integer powers of h bar, that means we can have a half integer genus. So I'm also going to allow for something like this. And of course the notation here is going to be exactly similar. So note that this is also an unstable correlator. 2 times 1/2 plus 1 minus 2 is 0. So this is not a stable correlator. That means that this is going to be part of our initial data. Finally, we also, yep. 1, because the 0, 1 is already in this Q. So, okay, no, I mean, it depends a bit on notation. Actually, maybe it's nicer to add Q mu dz over z if you like. Do you like this better? Okay, we'll do it this way then. This is perfectly fine. Actually, this is, yeah, probably geometrically this is better. So yeah, the leading coefficients is already fixed over here, and the other ones I'm going to write like this. Thanks. Now, for omega 0, 2, of course, we need 2 arguments. So that's going to look like this. We also know that omega 0, 2 will always have to have this double pole on the diagonal. So let's start with that. Now, of course, for a diagonal, we also need the sheets to be equal. And then it's just a standard thing. And we've got a large sum. Oh, sorry. So this is a bit of writing, but it's extremely analogous to what I wrote before already. So we just need to prepare all of this because this is going to be our initial data. Now, how do we actually introduce these initial data? Well, I said something about the dilaton shift and conjugation, and that's what we're going to do. So there are 3 things we can do. So first, let me define T. And T is going to introduce the omega 0, 1 and the omega 1/2, 1 into the story. So here you'll start to see the correspondence between the geometric picture and the algebraic picture. I'm just going to put all of these coefficients in here. But now I'm actually coupling them to modes. So these are positive modes. So that means that these are differential operators, right? They're actually h bar d times the differential operator, but then we're dividing by h bar. So this is something of, wait, sorry. I've already got the negative powers there, so I shouldn't do it like this. So you should see that this combination, you've got h bar to the -1 times the degree. That's actually of degree -1, and this is of degree 0. And what we're going to do is we're going to conjugate these WIKs with this thing to get something of lower degree, and that's what we wanted. So we need to conjugate with something of negative degree, because otherwise we're never going to get lower degrees. I'm also going to have to conjugate something more to get these in. And it's a pretty similar story. And then the definition of our Airy structure, possible Airy structure, we should say, is that, well, we take our W, this is the thing we had, which was homogeneous, and we conjugate with these 2 things. So we set a T inverse T, oh, other way around. And a phi. And if you paid attention to Kento's lectures, then Kento gave Virasoro constraints. That was some kind of half of an algebra. This is going to be similar. So we're not going to take the entire thing. In Kento's notation, the entire thing like this would have been the sum over the LMs times, well, dx squared over, well, so he would have had something like this, sum over n in z n ln dx squared over x to the n plus 2. Not quite, but then he only took part of the modes, right? Only the ones that were -1 or higher. We're going to do something similar. So we're going to take only part of these modes. So I should also decompose this. But actually, the selection of which modes we need is going to be hard. So first, I'm going to give you some more concrete description of what these ages are. So my claim is that certain subset of these modes will form an array structure under certain conditions. And then they will also have a geometric interpretation in terms of actual spectral curve topological recursion. Of course, you can see that a bit because we've prepared it in this way, but that's just notation up to now, so you need to actually see it. One thing I would like to note is that in an array structure, we had this solution that had FGNs in it for the stable GNNs. And this is quite nice because we also introduce the unstable ones and we conjugate by them. Well, to get the entire solution, we have to conjugate by all of the stable modes. So I know, heuristically, I find that kind of appealing. Do with that whatever you like. Right, but for now, this is just a definition. And considering the W's were already horrible, just imagine how bad these will be, right? And the question is, so there are now basically two questions remaining. One, how do we see this as actual TR? And two, in what case do we get an array structure? Because we want an array structure to actually have this symmetry condition. So let's write that down. When are HIK an array structure? And question two, how is this TR? And I'm going to answer the second question first, and then hopefully have some time left for the first question. I think I will. Also, so what I'm going to do is I'm going to write out H. That's going to be bad. But I'm going to start rewriting it in such a way that we get more and more known terms into it. So more and more things that we recognize from topological recursion. And that will not necessarily shorten the equations at first, but it will in the end. At least it will make it more recognizable for you, I hope. Right, so recall I had this thing here, J mu x, right? I would like to decompose this into three parts because they kind of behave differently under this conjugation. Just note that, maybe this is a good thing to note, in these conjugations we only have positive things like this. So what does this do? It shifts the negative modes. The positive modes are unaffected, and the negative modes do change. So in that case, because of that, it's kind of useful to distinguish between positive and negative modes. Also, I would like to introduce one piece of notation, which is S. This is the smallest k such that it's F0, 1, sorry, S mu. It's the smallest one such that this is not 0. So this is the leading exponent in Y, or rather in omega 0, 1. And if you recall, I gave you this counterexample before where for one particular S, our spectral curve did not actually give TR, for another one it did give TR, so this S is going to be quite important. Right, for now, I should start writing Zs now. So these are, J plus is the set of negative modes. Sorry about that, but those have positive exponents. Wait, this one may be better. So first of all, note that we had these fractional powers of x in these j mu's. And that's why I've switched to z, because on the mu components, we have this z, which is the appropriate root of x. So this is the right z to make sense of this. And these j minus actually has the positive modes. And we have the zero mode as well. Sorry, like this. Now, with all of this notation, I'm going to actually rewrite Wi. And it's going to be a mess still, but the mess in slightly more recognizable language, at least. So that I will take it as an improvement. The sum is the hard part, but what are we going to do? We have, well, we're basically going to sum over the fibers. So summing over fibers is something we do a lot in topological recursion. Recall that we had this Bouchard-Hénard formula, which was basically summing over all subsets of a fiber. This is going to be here, but I'm not writing it down yet. We have components omega 02 standard, which I should also introduce. So the standard is really just the part that we always have. So this is omega 02 standard. So recall that we, in this horrible expression I gave you before of Wi, there were these psi's, and these psi's had some sums over roots of unity, but at least there was some kind of 1 over x, well, z minus w squared thing going on. And that's basically what's in here. We've got a couple of these. So the next thing I'm going to do, we had this basically, we had the size, and then we had a normal ordered product of j's. And these j's, I'm not now going to decompose into 3 different parts. So we'll have the zero modes, we'll have some positive parts, and we'll have some negative parts. Now I don't quite want to write what we're doing here, but what we're doing is we take this point x. So x now can be seen as a projection from this curve that I just erased, but was here. So in particular, we can look at its inverse images, which I guess is getting annoying notation. I'm going to call this xi. Now we have a function x, so we can take the inverse image of a point xi. And I would like to decompose this into, well, a0, a plus, a minus, and p. But p is kind of annoying because it's a set of pairs. We always need 2 arguments for omega 0, 2, and like to write that properly is too much work. But the idea is that we take a couple of pairs, we put them in there, and the remainder we divide into these 3 different parts. So this is just a rewriting of the previous formula, but it looks fine. It has some advantages for us later on. But now mostly what happens if we conjugate? Right? We wanted not the w's, we wanted the h's. So maybe let's see what happens. We can now act on all of these 3 things independently. So actually, no, let's do everything. We have these 2 different conjugations. Let's see what happens. So yeah.
Have a sum, which is over pi, and then you have a product over not pi.
P, yeah.
And then a product over x.
Yeah, so as I said, I was a bit sloppy here. What I mean to say is that we have this fiber. We want to decompose it into 3 sets and a set of pairs. And it's, I don't know, I really don't know good notation for this. It's annoying. But the idea is that we distribute all of the elements of this fiber to go into here, 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 and here. And if you know better notation, then please tell me, because the notation we have in our paper is horrible.
They use something else between a0, a plus, a minus. Like these pairs, you have to consider points on this, right? So, like how you take those, like especially points under the products.
Yeah. So, okay. Now I know. Okay. I'm gonna say P. No. It's not going to be clearer if I actually write this out, but okay, if you really want me to, I'll do it. Is this better? This is okay, this is still not nice, but this is a collection. So we have a curly P now. Curly P is a collection, is a set of pairs. So all of these are 2 elements. The union of these elements of the curly P, disjoint union with A minus, disjoint union with A plus, disjoint union with A0 is the fiber. And here, for each P and curly P, we put the 2 elements, which are the elements of P, as the arguments in omega 0, 2. No. So for each omega 0, 2, we get 1 h bar. Right, yeah, sorry, this is It's just horrible. But we're just distributing all of the points in the fiber to one of these things. That's it. Yeah, we have to go through this, I'm sorry. But
you fix your sum of P, and then you're summing over all possible pairings, or like two-set partitions.
I guess, yes. If you like, it doesn't matter. There are many different equivalent ways of saying it. That is one valid way. It's not even that important, but okay. It happens. So, what was I saying? Well, we have this, right? We have these conjugations. And, well, we also know this conjugation. Commutation, I should say. This is h bar delta mu mu delta k plus L 0 times k. And we'll want to see how this acts on each of the individual components because it's just a large sum of products. And of course, I've set up the notation such that this makes some sense. So we need to look at these three parts. So basically what happens, what T does, T actually brings, so the negative modes, it turns the negative modes into just adding all of this. Because, well, we have the positive modes here, and because the positive modes only pair with negative modes, it turns the negative modes into something. But the negative modes are in J+. That's just the way it is. And because of Cantor's comment, we now actually get an h bar coefficient, which is not quite omega 1/2 1, but because we already had q, we need to subtract that now here. And we get omega 0 1. Another thing that happens is this is the only place where it's not quite true. This just changes into the actual omega 0 2. And finally, good point. That is actually a typo. Thank you very much. This should actually be subsets of size I. Thanks. That was actually a mistake. So the size of this thing . No, it's not making it better, is it? We'll get there though. Yeah, thank you. By the way, on the exercise sheet, there will be some formulae as well for you to check. Like, I'll just put them on there because I can't be bothered for you to. I mean, I can't assume that you actually remember all of them by heart. So I'll put them there for you to use in the exercises. Because I just know this is very formula heavy and there's no way around it, but we have to do it. Anyway, the point of all of this, yes, there is a point, is that this is starting to get closer to actual TR. So depending on what you know of topological recursion, you may know that these Deek size pop up everywhere, and they are what's called a polarization. So the polarization is related to what I told you before about the projection property. The projection property basically tells us that we can project everything that we're working with to a particular Lagrangian subspace. And this particular Lagrangian subspace is actually given by these Deek size. So this is a certain basis that we have. And this, as you can see, this basis is actually given by omega 02, so that is B. And that's how it relates to the projection property that I gave you before, because that was also a projection along B. Okay. Yeah. Yes, although it may have to be it should be a -1. L -1 dz, yeah. Also, I think if that's all possible, I'm going to scan my notes and maybe you can read them. I'm not sure.
Is that sum over U?
This one, yeah, there should also be a sum over nu, I guess. Thank you. That was actually not even in my notes, so very good. Now, what you can see, of course, is that if we do this entire conjugation, each of these individual parts will just be conjugated in this way. We can reorder things a bit, though, and I will. In terms of C, yes, I can. Not going to. You can do that. It's not useful for the flow of the story, so. But yeah, it's the thing you expect or you want. Or I mean, actually, I'm going to use it implicitly somewhere. I'll tell you when. Yep. Right. So the negative modes are multiplication modes, and the positive modes are derivation modes. Yeah. Yeah, that's quite important because that's how we got this, right? We started from the W's. They were elementary symmetric polynomials in the modes, and then what we did was we normal ordered them, and that's how we got all of these contributions from omega 02 standard. Yeah, thanks. Mm-hmm.
Two negatives, right? New and new.
Yeah.
And then so Deek C.
So you get a Deek C with a positive index and one with a negative index, but I'm not going to introduce all of those, which is why I don't want to do this. I mean, okay. I can give it to you later if you like. Right, but what you can see now is that if we just do all of this, well, we do all of these shifts. If we do it in a slightly nicer way, we see that we get, basically we replace all of these by omega 1/2 ones. We get things like this, and we get things like this. And of course, we also replace that by that. So I'm definitely not going to write out this sum again, just so even if you ask. We still have this. Now we have a product over omega 02. So it's going to be very sketchy, this, but okay. We have product of omega 01s now because we have that shift. We also have a product over omega 1/2 ones with h bar to the power 1/2. We still have the j pluses. And we have, I should give these curly j minuses. just going to define this to be curly j minus. That's all we need. Oh, that's a horrible j. So I didn't really do anything here. I just plugged in this into that. But now, what I did do, I mean, what's the point of all this? Is that we have things that are not homogeneous here. Right? Because this is actually of degree 0. You see that if I write this slightly differently, I'm going to move these h bars here. This is of degree 1 still. Sorry, this is of degree 2 actually, because h bar is of degree 2. This is of degree 1. This is of degree 1. This is of degree 1. But now this is of degree 0. So that tells us that some of these summands may actually have degree 1. Some of them may even have degree 0, which is a problem. We don't want those. But we do want things with degree 1. So at least, possibly, this could give us an Airy structure. Okay, so that's one upshot. Second upshot is, well, suppose this were to give us an Airy structure, then what does this tell us about the partition function? Right, that's what we want in the end. We want this partition function to be related to the output of topological recursion. So what happens if we have this act on the exponent of some f? Now that's not a very straightforward question, because these things are complicated, as you can see. But I'm going to do it anyway, because that's how it goes. Is there a question here?
Yes, but
Okay. Right, so we still have this formal function f. I'm not going to rewrite that, but I'm going to define now yet another thing. I guess I used size here, right? I should use more size. So for an Airy structure, we want to find an f such that this is 0, right? This was a definition of the partition function of an Airy structure, and supposedly this is unique. Well, we proved it's unique if it's an Airy structure. So I'm actually first going to assume that this is an Airy structure and then see what this tells us about f. And actually, I'm not going to, as I said before, similarly to Kanto's talk, I'm not going to take the entire G of psi. Rather, I'm taking about half of the modes. Now, of course, half of something infinite is not very well defined, but I'm going to assume rather that this is going to be O of x to some power. And if you think back all the way to the first part of the first lecture, there we also saw that we had this way of rewriting topological recursion to have, well, what we had was we had this symbolic thing that some sum over residues, some integral over b, 1 over y, and some complicated combination of correlators. This had to be 0. And I claimed that one way of doing that was, well, checking the order of vanishing of y, and then just ensuring that this complicated thing also had the right vanishing order. And that's what we're working towards. So this vanishing order is going to have something to do with the vanishing order on this side. Right, but first, what if we calculate this? That's going to be hard, right? Well, it turns out it's not that bad, because most of these things here, most of these terms are actual functions. And f is also a function. So most terms actually commute. It's not that horrible. Still not great, but it's not horrible. The only thing we could possibly have is sorry, let me write that here now. I think this is not going to be a trivial thing because these negative, sorry, this J minus has the positive modes in it. So those are the differentiation things. So we know that this will be something with a commutator. And this is the only thing that can happen, really. And also, note that in the end, we have this operator, we conjugate, and then we act on 1. So every one of these things, at some point, will have to act on f, because otherwise it just vanishes. So the only thing that we can get are iterated actions of this J minus on f, which is still a bit of a hassle to write out. And I think I'm going to skip a few details. I can give you an exercise on it if you like. You probably won't like it. But the answer is not too bad. So actually, I'm going to rewrite it a bit. So let's say what we can do is, whatever this will be, it will be some kind of function, right? We're going to decompose this as we're used to. Like this. Now just remember, I mean, what do we usually use these labels for? So h bar has some power g. That's what this g is. N means that this is going to be a homogeneous polynomial of degree n in these x mu k's. Now that's still not quite topological recursion because topological recursion has no x mu k's. What is that? We still need to get rid of those to make sense of this. But that's not too bad. Actually, what we can do, because this is basically what these curly j's do for us. These curly j's, if they act on a degree n polynomial, well, we have one derivation, and it turns it into something which actually lives on the spectral curve. So every time we act with one of these things, we turn a formal variable into an actual thing on our spectral curve. So if we have this decomposition, and we look at the degree n components, we have to do this action n times, and we get something. That's the story, at least. So I'm going to define yet another thing. Now, notation is starting to converge. So what I'll do is I'll take the adjoints. So I'm preparing some spectator variables, which you've seen before. These are just some other points on our curve. And I'm introducing them by taking the commutator of this curly j thing, acting on g, I, g, n. I should probably just write x here. Now, okay, this is a lot of technical machinery, and you may not quite understand what's going on, and that's completely fine. But what we're doing here is we have this thing, then we have it act on these f's. And recall that f, I should probably recall this. So f was a sum h bar to the g, which is just the same as there, n factorial, some lots of of things here. I'm actually going to write it this way now. Oh, wait. So this is just a shape we get from the theorem on area structures. But we want to reinterpret these FGN as the theta coefficients of our multidifferentials. And how do we do that? Well, we need to replace all of these x's by the Dieck size. Why by the Dieck size? Because those exactly give the basis of the space where multidifferentials can possibly live. How do we do that? Well, via this operator J minus, because J minus basically takes an x or an x mu k and turns it into something living on the spectral curve in the form of Dieck psi. So every time we have this conjugation and this happens, then, well, if we still have n elements of this type left, we still have to do n more conjugations. And that's how we turn this algebraic story into a story living on our spectral curve, so a geometric thing. And that is really what's going on here. So E is just the geometric version of G. I see some people are not very convinced yet. I think I'll add 1 or 2 exercises to the exercise sheet for details, but...
Just conceptually, what is the role of IPhT-TV?
Right, so depending on where you want to go, so the origin of omega 02 was coming from the conjugation we had elementary symmetric functions of these currents. We wanted to make it into a normal order thing. The commutator gave us this omega 02. And at this point of view, I would say it's just we needed to add all of the unstable correlators. That's how H is built up and omega 02 is in there. So from the VOA point of view, it comes from normal order, and towards our goal, it's just the way to implement our unstable correlators. Right. Actually, that's not quite true. The normal order is the standard part of omega 02, and the other part was by this conjugation, right? We had this conjugation which just explicitly put in all of our unstable correlators. So that's how we got the rest of omega 02. Now, okay, so this is basically it. And then we want to say that this is a vanishing order in X of some certain power. And we want to relate that to this formula I just wrote down here and see that we get 0 of the residues. But now the question remains, because I kind of bracketed that question, is this actually an Airy structure? And that is quite a big question. It's still not easy. We've now set up all of the notation, so at least we're not going to do more notation. But this question is still kind of hard, because what we want to do, we want to say that we take some kind of index set. We have these HIKs, and the question is set of HIK for, this in some index set. Is this an Airy structure? And the answer is sometimes yes, sometimes no. That's not a very satisfactory answer, so I can give you some conditions. But this is at least the story going from Airy structures to topological recursion. And now we need to check when that story helps us. So maybe it's good to see if there are any questions about this part. If there are too many questions for you to even be able to phrase them, that's also fine, and there will be exercises on this. So. Right. Okay, so let's just recall a bit on the TR side. Let me see. Yeah. I think it's time to go to section 3. So first of all, let's go back a bit to what I wrote in the first lecture. So we had this sum over all ramification points of the residue at that ramification point of, well, there's basically a projection operator, the integral of b. We divide it by this capital Y. And then we have this, well, still pretty complicated sum, omega g I n. So we had a subset, we were taking subsets of this fiber of Z at A, right? Actually, this was the size of Z here. Then we put in these elements. We have these spectator variables as usual. And then we have this part. Actually, there was a prime here. So you don't need to write this down because I've already given this to you before. You can still write it down if you like. So first of all, one exercise is going to be, sorry? Right, so F was the entire fiber. F prime is the fiber minus the element itself. So all of the conjugates. Oh, right, sorry, I used a different notation for capital Z. That's it. I forgot about that. Right. Is this better? And then it should also be in here. There we go. Thanks, I completely forgot about this. Yeah, sorry for the confusion. So one exercise will actually have you show that this is equal to this, which I just wrote down there. So that's a good sign, right? I'm not going to do that here because it's combinatorics. Combinatorics is fun, but it's not fun to do on the board. So next thing, we still have these dots there for the vanishing order of this thing. And what I said is I want to basically, well, to base this vanishing order on the vanishing order of this y. So that's the other thing we should look at. This y was defined to be just a product over all elements in the fiber, or, well, all elements in the fiber except for the trivial one, of the difference between omega 0 ones. I think I should write it like this. Now the question is, what's the vanishing order of this thing? And actually, honestly, this is also going to be combinatorics, but it's not, I can give you some pictures for this actually. So we should now start thinking about this. Well, I've defined these omega 0 ones. I mean, no, rather I've defined Z mu to be such that this has leading order Z to the S mu minus 1. That's the definition of S mu. So it's this, slightly more concretely, it's this for some kind of non-zero t plus OZ to the S mu, of course, times dz. So this is nothing much, it's just the definition of S mu and the definition of T mu. Right, but to think about vanishing order, here it's kind of important to know that Z is not always of the same order, because on different sheets, Z is a different root of X. Because, recall again, we had this X minus Z to the R mu on sheet mu. So for the vanishing order, this is actually getting important especially if we have z and zeta on different components. So if you actually want to calculate the vanishing order of this, you have to take that into account. Now, the exact order is, well, it's a bit of a hassle to think about, but it's not that hard. And what's kind of nice is that what you should do is you should kind of be greedy. If you want to get the vanishing order, you should take, well, you should take as little vanishing as possible at each possible step, right? Well, no, actually, it's not necessary for this one. For this one, it's even easier. But right, so let's see this maybe in terms of x. What's the vanishing order of this in terms of x? Well, this one will be order x to the power r mu over s mu minus 1 dz, which is still annoying, right? I'd rather write this as, I'm going to write it like this, dz over z, but then this is dx over x. This is, of course, if this thing lies in mu, and let's say this lies in some nu. So just to recall this notation, if I use this, I specify that mu lies on, that z lies on the muth component. Now we can do something similar for this one, right? It's just going to be the same formula, but then we have mu's instead of mu's. But the vanishing of the difference, that will be the minimum of the two, right? Unless these minima are actually equal, in which case they may still cancel in a certain way. Right? And that makes things slightly complicated because we have to distinguish cases all the time between which one is the smaller of the two. Well, which one is the smaller? Rather, which one of r mu over s mu is the smaller? Because of that, what we usually do is we take some kind of ordering of these components just to make our life a bit easier. So from now on, I'm going to say that mu is larger than nu if r mu over s mu is at least r nu over s nu. This is just something I can define. Right? I can define a total ordering on the components such that this holds. May not be unique, don't need it to be. Now, with all of this, you can actually calculate the order of vanishing of this thing, which again, I'm not going to do here because it's more of an exercise thing. But I think I've written it down somewhere, so I can give you the conclusion. Should have written it down somewhere. There we go. And you can see that this may actually depend a bit on, well, what S and R actually are. I mean, of course, it depends on that a lot. But there are lots of different options here. So first of all, we could be very unlucky. And this function y can be identically 0. That would be a problem, because if y is identically 0, this does not make much sense. So we don't want that. So we get a condition. So we do not want y to be identically 0. How would this possibly happen? Well, for y to be 0, one of these factors must be 0. That can happen in several ways. But in our notation, this means, well, we exclude the possibility of r mu larger than 1 and s mu being infinity. just to note, S mu in principle can be infinity. This means that we do not have a dilaton shift in this component. This means that omega 0,1 is identically 0. That sounds a bit trivial, and it is a bit trivial if that's the only component there is. But it turns out that we can in fact have this, and it's like there is an actual example of interesting topological recursion where this happens. But that does require that R mu is equal to 1 there. So this we must exclude. We of course also must exclude 2 R mu's equal 1 with S mu equal infinity, because that would still give us 2 omega 0,1s that are 0. We can't have that. And we must also exclude, well, another issue that can happen is that this vanishes to a slightly larger order than you would get from this naive checking, which is just if these have the same vanishing order, but their leading coefficients actually vanish. That could happen. We will exclude that for now. Actually, we will exclude that for the rest of the talks. But this could probably be one of the points where our classification is not strict. So I'm going to say we'll exclude it for now, but later on, maybe interesting. For now, this is the condition that we have 2 mu and nu, such that, well, these vanishing orders are equal. So R mu over S mu is equal to R nu over S nu. And moreover, these leading coefficients are also related. In this way. So all of these conditions tell us that basically this Y vanishes to the naive guess order. Otherwise, we have to be more careful, and this is already enough of a mess that we don't want to be more careful. So we're not going to do that. But these are somehow fair. Another thing, we also really want R and S to be co-prime. Because otherwise, even within one sheet, this can already be problematic. So let's also exclude that. So these are pretty naive exclusions, right? These are things that, just from a geometric point of view, we really don't want because something very simple in the assumptions of TR goes wrong already.
This morning you drew one
Yeah.
This is okay.
Oh, we can have as many R mu's equal to 1 as we want. We just don't want omega 0 to vanish identically on them. So that's this condition. Yeah. So S mu is equal to infinity means that there is no non-zero coefficient of omega 0,1. But we can easily have many unramified components where omega 0 is non-zero. That's fine.
Then could you have compensation?
Sorry?
2 omega 0,1s on different sheets compensate?
Yes. And that is exactly this condition.
GCD greater than 1?
Yeah.
Don't have that.
Yeah, so then what would happen? If that is actually greater than 1, we could have, so suppose it looks like this, right? Actually, I'd rather write it like this because this form is nicer. Then you can see that for different values of, so the sheets of this, well, on this component are just given by multiplying z by an rth root, right? But if S and R are not co-prime, then two different rth roots will have the same S power. So again, you would have the issue that these leading orders will cancel against each other. And that is why this last condition is necessary.
Wasn't that also supposed to be related to the symmetry?
To
The invariance?
I mean, yes, because everything we do is related to the symmetry, in the sense that all of these conditions are somehow needed for us to, at some point, hopefully get an Airy structure. But that's it. Yeah, it's even before that. But there are, so should note that these are not going to be the only conditions, because I did write a counterexample that does satisfy all of these conditions. So there are still more conditions to follow, sadly. But actually, what I can say is that this is actually sufficient to get the degree 1 condition of the Airy structure, which actually, so how much time do I have left? I have no clue when I started. Sorry? Oh, okay, great. Good. That's what I thought, but I wasn't sure. So I'll have some time to talk about that. But it turns out that for the degree 1 condition, this is basically all we need. And maybe I should say, yeah, this basically tells us that at leading order, omega 0, 1 separates fibers, which is a fair condition to have. Geometrically, it makes sense that if omega 0, 1 does not separate fibers, well, then this y just becomes problematic. Yeah?
Just to be confused, when you write a big O,
Big O, yeah. Yeah, it's all, oh, right, yeah, I should say that. So in this formula, I don't make that explicit, but like all of the algebraic story is taking a branch point at 0 and looking in the vicinity of that. Yes. Thanks. Right, okay, so we will exclude all of these. And now I want to show actually that the degree 1 condition is satisfied. I'm not going to say too much about the subalgebra condition because that's, I think, well, that basically uses a lot of VOA knowledge, so I can't do much with that. But this I can say something about. Right. Okay, so let me just take a moment. And go ahead in my notes. So given all this, we get a certain vanishing condition here, which I still haven't written down. I was going to at some point. Actually, what I was looking for. Right. So excluding. So if none of these hold, then exercise, you can see that this is of some certain order. So I'm going to write it out and give you some idea of what's actually going on here. So there are two terms. The first one is basically the naive term you would expect from just writing this as well in this way. Sorry, this should be Z. It should be X, I think. No, it's probably right. So the first one would be just assuming that this is the leading order. So it's always the one from Z and never the one from zeta. But because actually what you're doing is you're taking a minimum of the two you have to compensate. And that you do by subtracting this thing where, well, R mu is defined to be, so with these brackets, it's the sum from mu equals 1 up to mu of R nu, and similarly for S. So basically, we have to divide between things that are larger than mu and smaller than mu, and we have to compensate for the ones that are smaller, I think. Never know which one's which. And that is what this formula gives. But it's actually something you can find without too much trying. Combinatorics is not too hard. Now, right, so we had these H's, right? These H's, they were some products of omega 0 1s, omega 1/2 1s, omega 0 2s, these J pluses, J minuses. There was a lot of stuff going on. Now what we want is we want them to be an Airy structure. We want to have this degree 1 condition, most of all. So let's recall what this degree 1 condition was. So first of all, I should note that this is not going to be an Airy structure in normal form. So we have to do some kind of linear transformation in general. So this linear transformation, so we have these, I should probably try a new marker. That's better. So we had these HIK, and we want to see that, let me do this in the right way. I have two matrices going on, I want to take the right one. Just a moment. Right, yes. So basically, I want to take the degree 1 component of this. So this is a projection onto the degree 1. And I want to see that up to a linear transformation, this is just going to be a matrix. This will be these things. More specifically, we want all of these with the positive A's, because recall, an Airy structure was something. Well, an Airy structure in normal form was one where H tilde mu A is H bar D x mu A plus order 2 or higher. Right, so what I'm saying is that up to this transformation, and I'm using some kind of summation convention, so there's some sum over mu and A's here. Up to this thing, it's actually these, which are equal to these. And moreover, this is actually an invertible matrix. That is what we want to prove. Now, it's going to be somewhat hard because we need to find some condition on these i's and k's. And these conditions on I and k, of course, are related to the conditions on the vanishing order, because k was basically the power of the HIX. But first, what's actually nicer is to forget about this condition whatsoever. We're just going to take all mu's and all a's, all i's and all k's, and see that in that case we can go from one to the other. That is easier, and then we can try and actually restrict our summation range. So let's think about this projection to degree 1. We had this complicated product for HI, where we had, as I said, we had omega 0 1s in it, we had omega 0 2s in it, we had omega 1/2 1s in it, we had J pluses, we had J minuses. But almost all of these things are of degree 1. Omega 0 1 is of degree 0, everything else is of degree 1. Now what we actually want is we want one of these things which is in J minus. But nothing more than that. So the only way we can possibly get that is by having lots of omega 0,1s. And all of the other factors we don't care about, because they're degree 1 or degree 2, so whatever. So let me get that. Right. So we had this complicated thing, but actually I can write a slightly simpler thing. Because we will only have one j in here. We will still have this sum. Sorry, let me do this correctly. No, I should rewrite this entire thing. Sorry. We'll still do this in terms of generating series. So pi1 hiz, or x, let's do x. Right, this is the kind of thing we were looking at, generating series. And let me do xi actually. So what we can do is we take one element of the fiber of x, xi. We can take j of z. And all of the other factors must be omega 0,1s of z primes. So product of z prime in fancy z, where fancy z is again a subset of this fiber. Right, so basically what I'm doing here is, for this element psi, I'm taking one element in the fiber that's going to be in the current, and all of the other elements must be in omega 0,1 just because they can't go anywhere else. Otherwise, this thing would be too high a degree. Okay. This is, of course, quite a bit of an easier equation than the entire thing, but we don't need the entire thing. That's okay. Now, and if you look at this in terms of generating series, it's actually pretty straightforward to write down an inverse. This is something I can do immediately if my marker still works. Because actually, it's slightly nicer if we just add an extra formal variable here. And we can see this as some kind of, well, elementary symmetric function again, right? We're summing over subsets of a set, which we can think of as the roots of a polynomial. And we're taking products of all different elements in this set. That is basically an elementary symmetric function. So these things in here, these are nothing more than coefficients of a polynomial of which the roots, sorry, I should do it like this. These are just the ei minus 1 of the omega 0,1 z primes. And this comes from all the way from the way we defined our w's. But that is nice because we can actually invert this. If we have a polynomial with distinct roots, we can actually get something out of that. And I can write this explicitly for you. I heard that. To rebut that, I'm now using a formula that I learned in my second year of my undergrad. So this is probably the easiest formula of the entire lecture. Do with that whatever you will. Of course, it has some more fancy notation, but it's fairly easy. Basically, what we have, so remember that before we saw these elementary symmetric polynomials, we just added this extra formal variable u to make it into a polynomial. we could do the same here. So it's h xu is just the sum over u to the I h to the r minus ix, just a polynomial, where these are elementary symmetric functions, right, of the roots. And yeah, there's nothing much to it. If we know all of the other roots, we have a polynomial, we know r minus 1 of the roots, we can get the last one via this formula. It's just a very basic formula which you may have seen or you may not have seen it, but it exists. The point being that if all of the roots are different, we can get the last root from knowing all of the other ones via this formula. Of course, the condition being that all of these roots must be different, but we basically assumed that, so that's good. So this tells us that if we have all of the HIKs, we can return to all of the J mu A's, and vice versa. So that's already pretty close to this thing. I mean, that is this thing, rather. This is invertible now. I've just told you that. The only issue is that we don't want this to be invertible on the entire range. We rather want this to be invertible on a subset. Now that is a bit more complicated. But it's a good sign, right? At least it tells us that in principle we can invert something and we get something close to this degree 1 condition. The only issue is that if we take this entire set, the degree 1 may not be del, not be a derivative operator, but it could also be a multiplication operator. And we don't want multiplication operators in our array structure. Yeah.
The third condition you just erased.
Yeah. Should I rewrite it?
Y squared minus x and then square of that. Is that an example of that?
Yeah, that would be a problem.
Y squared minus x and you take a square of that.
That would be problematic, yes. That would, yeah, that's ruled out by this condition.
Okay. It's not just going to be simply double.
No, I mean, that would not separate fibers, and as I just told you, we need that.
Yeah, that's okay.
Right? So we definitely need our curves to still be reduced and stuff like that. Right. Oh, it's a projection on degree 1. So we have this grading on our Weyl algebra, and pi 1 is just the projection on the degree 1 part. That's all. Okay. It's not a fundamental group or anything. It's just a...
I was thinking of a fundamental group.
No, it's not. Yeah, I can understand why you would think that would be very hard. That would be very hard, honestly. I have no clue about fundamental groups here. But it's just a projection on the degree 1. Right? It's not scary. Good. Okay, so what do we have now? We have, I'm actually going to decompose this big vector mu, big vector j, which has a range of mu from 1 to d, and it has a range of a over all integers. So it's a very infinite vector. And I've got this vector h as well. So let's say we have, so we have a part of this mu that we actually like. So let's call that part, let me be consistent with my own notation. I should probably try and do that. Yes. Right, so I'm going to write j minus for the subvector of all these j mu a's, where a is larger than 0, j plus for the rest. And what this tells us is that we have some kind of, well, we also have some kind of vector h. And I want to somehow split h also in some h plus. Where this is in some index range that we still have to determine. And some h minus, which is the rest. What we have now is we have some kind of formula that symbolically we can write like this. And we know that this entire thing is invertible. And that's as far as we got. Now what we actually want to show, actually what we can see from this definition, right? We see that if we only take the j minus part in here, we will not be able to reach all of the HIKs, just because these are all bounded from below by definition. So if we start from something in j minus here, that means that we get a certain bound on z here. We also have a bound on z here. That gives us a bound on, on the degree of z in each of those. That gives us a bound on the degree of the psi here. That's just adding orders. Nothing hard going on. And I'm basically going to take this I here to be that particular bound. That helps me because if I do that, I can take this to be 0. So this tells us if we pick I in the right way, we can always take this to be 0. I think the markers are kind of starting to run out. This is good. So this tells us that H minus is M minus minus J minus, which is good. But there's still an issue because we don't actually know if M minus minus is invertible. If this were a finite matrix, that would be the case. But it's not. It's infinite. So we do have to actually do something more. We have to write down the inverse of this thing. So let me do that like this. We also have some other matrix, which is called N. This now, of course, is the most. Oh, I shouldn't have done it like this. Sorry. And now we want to show that this thing is also 0. Now I'm not going to do that explicitly here because it's basically a lot of manipulations of this thing. So this I over here only defines somehow implicitly such that this is 0 by saying we take exactly the right vanishing order from all of this to get the right case here. It turns out that if you do some complicated manipulations, we do actually get that n plus minus is also 0. And that is sufficient to tell us also that j minus is n minus minus h minus, so that these blocks are in fact each other's inverse. And that gives us a degree 0 condition. Sorry, degree 1 condition. The degree 0 condition is even easier. There will just be 0 for this range. There will be some exercise on that. So this basically tells us that because everything is set up nicely, we have now got the right range for what is possibly an Airy structure, and we have the degree 1 condition. Turns out also that this range is actually compatible with the abstract loop equation, so with the vanishing order that we naively got from this y, which is not too surprising because actually, if you look at this thing here, which you may want to use a different color for, this thing here looks surprisingly quite a lot like y, right? because actually, if we fill in this, it is y. So that's not too much of a surprise. Actually, probably if we had realized that earlier, we could have made the paper quite a bit shorter, but anyways, we didn't. So sorry about that. But so the degree 1 condition is very well connected with the form of this y. Now there's this other thing, which is called the subalgebra condition, and that is an issue. I mean, that Yannick agrees with me, I think. That is a big issue. And that's why I'm not going to say anything about it here, except that recall how we calculate, or how we got these h's. These h's were made from conjugating, right? We conjugated these w things. Now, of course, if we have a subalgebra in the w case, we have a subalgebra in the h case, so we only have to think about these w's. Now, that is still arcane magic to me, so I can't do it. But luckily, the first paper I cited, Nitin and co-authors, did quite some of that. So basically what they did is they gave us quite a couple of subalgebras that actually exist. And what we did in our paper for a large part was checking when the index that we got from this story it actually agrees with one of these subalgebras. Now I can give you a theorem about that. So maybe I should, because I haven't given you any theorems yet. And then I have some time for applications even. Right, theorem. So we have some numbers, R1 up to Rd, which are at least 1. Natural numbers. We have S1 up to Sd, which are also at least 1, but we want to allow them to be infinity. We also want to have Q1 up to Qd complex numbers and T1 up to Td non-zero complex numbers. Well, we don't want any Td if Sd equals infinity. So. And then we have quite a few conditions. So first of all, I told you something about this sum, Qi's, or Qmus, I should say. This should be 0. I also wanted this condition before, right? So if mu and nu are different, but R mu divided by S mu equals R nu divided by S nu, then I wanted something about these leading coefficients. And right, I ordered them in a way before, right? So I'll actually say I want to have R mu and S mu, I want them co-prime. This is a condition we saw before. And also, if we order them, so we say R1, S1, we order them like this. This is something we can do. So these are all things I've actually written down before. I'm just writing them as conditions now. Now it turns out there are some more conditions which are kind of weird. So we want R1 to be -1 modulo S1. We want S2 up to SD to be equal to 1. And we want RD to be 1 modulo SD. Then we get an area structure. Now, okay, this is a lot of things to take in. The point being, there exist some reducible area structures, and I can give you a few examples. I have like 15 minutes left, right? Good. So there are quite some weird conditions here, and we're not sure if this is all. There could be slightly more, but probably not much more. We did actually do quite some calculations on unstable correlators, or sorry, on low Euler characteristic correlators, and found that if this doesn't hold, in many cases, it is actually not symmetric. So it's kind of close to the theoretical bound, but they're not quite equal yet. So maybe let me give you one example that actually has some meaning, because otherwise this is really just abstract nonsense, which not all of you may like as much as I do. So, okay. So note particularly that one of these s's may be infinity. Exactly one, right? Not more than one, at least. If one of these s's is infinity, it must be SD, because in that case this fraction will be 0. And of course that actually holds, because if like RD being 1 modulo infinity, that just means RD equals 1. That's a condition we've seen before, so that is all consistent. And it turns out that the spectral curve x minus y to the r times y equals 0. This is a perfectly well-defined spectral curve now. We know how to do topological recursion on it. And I'm also going to say Q1 is not 0. Of course, it's going to be equal to minus Q2. So, oh yeah, sorry. This is going to be branch 1. Because I need to label things now. So, in coordinates, this means that x1z equals z to the r, y1z equals z, x2z equals z, and y2z equals 0. This is what this formula tells us. This is perfectly well defined. We can do TR on them, on this. And this actually supposedly calculates something for us, which is, it's still kind of conjectural. But, well, you've heard quite some things about intersection numbers on moduli spaces of curves by Newton's story. It turns out that supposedly it's possible to construct an extension of these things, which is a moduli space of open curves, where open means that we can have a boundary. So, for example, we can have a disk. Well, a disk is not actually stable, so let's give it some interior point, maybe some point on the boundary, another point on the boundary. We can check, like, calculate the moduli space of these things, for example. And similar to the story of, of closed curves, we also have to take care of boundary strata. But it turns out that probably it's possible to make moduli spaces of this, as in people claim they've done it, but they haven't published anything. But the interesting thing is that even though the moduli spaces haven't been published yet, Sascha Bujak has already conjectured an integral hierarchy for these, for the intersection numbers of these things that can be defined in a certain way similar to the closed case. And moreover, Sascha Alexandrov actually made these into some analog of VSORO constraints, open VSORO, and we managed to make that into a spectral curve. So basically, we already have topological recursion for numbers that haven't been defined yet, which is kind of cool. That's actually for the case r equals 2. So this is somehow, you just add an extra branch to the formula for the area curve. I guess Newton didn't say anything about Witten classes, right? Okay, so if you want to do more general R, that's even more fun. Even without the extra branch. This is great fun. And you get something called R-spin theory in the closed case, and there's also an analog of open R-spin theory, and we conjecture that this curve calculates these things. Now that's all very conjectural because these spaces haven't been defined and there are many issues. Or rather, the spaces have kind of been defined, but integrating over them is complicated because of orientation issues. But anyways, this does tell us that there is something going on here. One other thing I want to mention is that, well, I said something at the start about limits of spectral curves, right? If you have just a very simple spectral curve with simple ramification points, you may wonder what happens if these ramification points collide, right? This is a fair question. It's actually a useful question to think about. And it turns out that, well, for this question, it's still okay. But suppose you have, I'm going to, again, change markers. Suppose you have a spectral curve like this, for example. So this has two simple ramification points. And you could have these kind of tend to each other, right? Become closer and closer. Now, the right way of actually thinking about this from a TR perspective is, well, you don't want to just take a neighborhood over here, and a neighborhood over here, but rather you should take this entire fiber into account. So you should actually think about this and this, and then try to collide these things. Now, in this particular case, well, I haven't actually given you a case, but this is just a doodle. But the idea is that you have to take care of the ramification points and all of the other conjugates. And moreover, you need to be very careful what happens if these things join, because, well, if you have two local stories and you want to join them together, it becomes a bit complicated. So this is all not quite clear what happens in general limits, but this is something that's work in progress. So this story is, let's see. Oh. So lots of people are working on this. So the idea is that, well, the kind of area structures, well, we still need to have conditions all over here. I should not forget Sergey. This is work in progress with these 5 people. And so if we take limits, we have to know, first of all, what happens in a general fiber. And then this area structure point of view is very useful because it actually tells us, in the case of complicated fibers, when this can be symmetric. And then we also have to do something about, well, merging things, which is yet another issue. But that's somehow an outlook. And this is one way of approaching part of these issues. Right, so that's almost it. I just want to say one final thing, which I just find kind of neat, and you'll also find this on the exercise sheet. So we have this, if we think about, say, this thing, right? If Q is not equal to zero, then something interesting happens. But this sheet, apart from the Q, it doesn't do much, right? Omega 0, 1 is 0 here. Actually, this has also got the standard omega 0, 2, so there's not much interaction. The only interaction here comes from the omega 1/2 1. But what if we turn that off as well? Turns out that if you have a component on which omega 0, 1 is 0, and omega 1/2 1 is 0, and moreover it doesn't interact with the other components via omega 0, 2, then we can just get rid of that entire component. So if we have a component where all of the unstable correlators vanish, then it doesn't contribute to TR. And there's an exercise in the exercise sheets about this. which is it's also kind of a nice consistency condition, because in this story, Q is supposed to be a formal parameter which parameterizes the number of boundaries. So this would be a disk, but you could easily have, you know, a cylinder, which would have two boundaries. So that would go with Q squared. Oh, that's a horrible painting, a horrible drawing. Sorry. So of course, if you set this formal parameter equal to 0, you do want this component to decouple because you want to go back to closed surfaces. And it turns out that from the topological recursion perspective, that actually follows. So that's an exercise you'll do not tomorrow, but the day after tomorrow, because tomorrow we're going on a boat. And that's about it for now. So I hope you'll look forward to the exercise sessions. I know I do. And thanks. Yep.
So I have many questions. So if the claim or conjecture that this spectral curve that you're bringing to the board, this is the spectral curve of open art.
Yes, that is the claim.
Because I may be able to compute these numbers live in the break-in.
That would be awesome. Then we can compare.
Okay, we should definitely.
Yeah.
And then also, did you say that these moduli spaces have to be constructed?
Well, as far as I know, so the modular space of disks has been constructed. The modular space of R-spin disks has also been constructed, but not for general GN. Well, apart from them having been constructed allegedly, but not having been published. So yeah, for disks they have been constructed, and everything does coincide.
But there's still more. I mean, these numbers, the ones from TR, if you descent plate.
Ah, right. Yeah, that's also a good point. Yeah. And that, I don't think anyone has a good clue on how to construct those geometrically at all. So it's quite exciting that we somehow get more than the geometry people. If you're just too overwhelmed with all of the formulas I wrote down, that makes total sense, and I'll hope the exercises will help you a bit. Yep. Yeah, you can just set omega 1/2 to 0. Sorry. So, what do you mean? Yeah. Right. No, you can really only have omega 0,1 equal to 0 on at most one sheet, because we had this degree 1 condition, and for that you needed to have this degree shift, and the degree shift really only comes from 0,1. So that cannot happen too much.
But it can.
It can happen on one sheet, and that's what's happening here, but not more than one.
Oh.
So on this one I do, because I've set Q to be non-zero, and Q is part of omega 1/2, 1. And I just said that if we also set that to be 0, then this entire component can be erased. Yeah. Yeah. And that also makes sense in this picture, right? Because you should count half of the double. So it's half of the double genus somehow. It's related, the double genus will still be an integer, but like whatever it is, the genus of an open thing is kind of unclear. I mean, what it means, so it's not quite, because what's the formula? Like the double genus, I think, is 2g plus b minus 1, where, so this should be 1, but this should also be 2. And so this would still have genus 0. I'm not quite sure. But there are definitely cases where you can get half integer, but I think this may have integer.
These number of boundaries.
Yeah. No, so that would also be fine. There are definitely issues somewhere. I'll have to think about that, but I can give you an example in a few minutes. Think about it. You can always ask questions later. I mean, you'll have plenty of opportunity.